Today, we're diving into something called the invisible line, that hidden, crucial difference between technology that seems to work just fine and tech that is truly reliable, especially when something as important as our health is on the line.
So think about the tech you rely on. Maybe it's a fitness tracker, a hospital monitor, or even a telehealth app on your phone. They seem to work, right? But what happens when there's a glitch, when things go wrong? Is a simple restart really enough to earn your trust?
Okay, take a look at this graph. It gets right to the heart of the problem. That green line, just cruising along at the top, that's a system that's consistently stable. That's what you want. But look at the orange and blue lines. They're way more chaotic. The real danger here, the invisible part, is that without the right way of looking, all three of these systems might seem perfectly fine, right up until a crisis hits. And that brings us right to the first big idea from this research, something they call the illusion of stability. I mean, we are surrounded by connected health tech, right? From the smartwatch on your wrist that's keeping tabs on your heart rate to the incredibly complex web of devices in an ICU, these systems are constantly making critical calculations. We put a huge amount of trust in them every single day. And that leads to the million-dollar question. If a network of patient monitors has a little hiccup, it glitches and then comes back online, you might think, phew, okay, everything's fine. But is it? Is that system now maybe a little more fragile, a little more noisy, or is it way more likely to fail again, for real this time? Just recovering might be hiding a much deeper problem. So to actually see that hidden instability, we have to look at how we've traditionally measured reliability. And for a long, long time, it really all came down to one thing: synchronization. You can think of synchronization, or R as it's called, like an orchestra tuning its instruments right before a performance. It tells you if everyone is playing the same note at that one specific moment. It's a snapshot. A high R value means, the system is coordinated right now, but it tells you absolutely nothing about what's going to happen next. And this is where you see the problem in action. Look at what happens right at that moment of perturbation. That's the shock to the system. The top green system, it takes the hit, it dips a little, but boom, it bounces right back. But the orange and blue systems, they really struggle. Sure, they might get back on their feet eventually, but their performance is clearly way worse. That initial snapshot of stability, it didn't tell us the whole story. Not even close. So it all boils down to this really powerful conclusion from the researchers. Just being able to return to normal, to get back online, is not good enough. It doesn't guarantee the system is actually reliable. Okay, so if the old way doesn't work, what's the answer? Well, this is where the researchers introduced their solution, a completely new way to score a system's true robustness. They call it Delta. And instead of just being a snapshot, you can think of Delta as a full, top-to-bottom diagnostic report. It's designed to measure not just if a system is working, but how well it's working, especially when it's under pressure. So how does Delta do this? Well, it's built on 4 key ingredients, kind of like a recipe for real reliability. First up is alignment. Just how well is the system performing to begin with? Second, persistence. Is that performance nice and steady, or is it all over the map? Third, shock robustness. When that crisis hits, how big is the impact? And finally, the really important one, recovery quality. Does it just limp back online, or does it bounce back strong and fast? So by combining all 4 of those ingredients, the researchers discovered something huge, a critical threshold, a line in the sand. And that number is 0.72. So what does that mean? It means if a system scores above 0.72 on the Delta scale, it hasn't just learned how to restart, it's become genuinely resilient. It's the difference between a house of cards that you can rebuild and a stone fortress that can actually withstand the storm. Okay, that's a pretty big claim. So how did they actually prove it? Let's dig into the evidence. First, they measured simple recovery. Now, this graph shows what happens as they increase something called coupling strength. Just think of it as how strongly all the different parts of the system are connected and talking to each other. Notice how at a certain point, right around 2.0, the system suddenly figures out how to recover. That's the recovery transition. It's the first step. But now, look at this. As that same coupling strength keeps going up, the Delta score, that's the orange line, it crosses our magic 0.72 threshold much, much later, around 2.4. This is what they call the robustness transition, and it proves that becoming truly robust is a much higher bar to clear than just being able to recover. And this chart just lays it all out, crystal clear.
You see that? There is a real measurable gap between when a system can restart and when it becomes truly robust. This robustness gap is the invisible danger zone. It's where a system might seem like it's okay, but it's actually lacking the deep resilience you need for a critical job. Another way to think about it is that they're asking two totally different questions. Other advanced metrics, like base instability, they're basically asking, can the system return, yes or no? But the delta functional, it asks a much tougher, more important question. How well does the system perform before, during, and after a crisis? It's all about quality, not just possibility. And this final piece of evidence is, I think, just fascinating. The blue line represents that old synchronization metric. See how it just hits the ceiling and flatlines? It basically throws up its hands and says, yep, it's coordinated, my job here is done. But look at the orange delta score. It keeps climbing. It continues to tell the difference between good, better, and truly excellent performance. It gives us a clearer picture right when we need it the most.
Okay, so we've looked at the science, we've seen the data. Let's bring this all back down to earth and ask, why does this idea of true robustness matter so much in the real world?
Well, the applications are pretty much everywhere that critical health technology is used. We're talking about those wearable monitors that have to provide reliable data 24/7. We're talking about the networks in a hospital ICU where even a moment of instability could be catastrophic. Telehealth systems connecting doctors to patients hundreds of miles away. Even the AI models that are helping doctors make decisions. All of these things, they need more than just recovery. They need real robustness.
This final quote from the research really just says it all. A system that just recovers might be hiding some serious flaws. It could be spitting out noisy, unreliable data, or it could be on the verge of another, maybe even bigger failure. True robustness means we can trust that system not just to survive, but to actually thrive. Which really just leaves us with one last thing to think about. In a world where we are putting more and more of our health and our safety into the hands of technology, we have to ask ourselves, when lives are well and truly on the line, is a system that can simply reboot ever going to be good enough?